So in the next part of section 3.1, we will be solving quadratics by taking square roots. But before we do that, we need to practice simplifying radicals or simplifying square roots because that's part of the process. So one of the things that we have is what we call the product property with simplifying radicals. And it just tells us that if we have two square roots, we can put those together into one. Or we can split them up. If we have some sort of factorable product underneath the radical, we can split it up into two separate roots. So some examples that we have here, we've got square root of 5 times square root of 18. We can put that together under the same root. And then I wouldn't multiply those together because you're going to try and break this down. It's a square root, so we want to look for groups of size 2. And groups of size 2 can come out of the square root. So I'm going to use a factor tree here. 18 is 9 times 2, and that 9 is really a 3 times 3. So I have a pair of 3s. Those 3s can come outside of the root, and it just comes out as 1 3 because the square root of 9 is 3. And then anything that's left over stays underneath. So I have a leftover 5 and a leftover 2. So 5 times 2 is 10. So my simplified radical here would be 3 square roots of 10. We can do something similar here with question 2. So I can put that together into 6 times 12. Again, I would not multiply those together because I'm trying to look for pairs. I could break that 6 down into 2 times 3 if I wanted, or if I recognize that 12 is 6 times 2, I can pull out that pair of 6s. So this would be 6 times the square root of 2. If I were to instead, say I did break that 6 down, so just to show you that way, I have square root of 6 times 12. This 6 is 2 times 3. This 12 is 2 times 6. This 6 is 2 times 3. Here's a pair of 2s, and then here's a pair of 3s. So the 2s and the 3s come outside of the radical. So I've got a 2 times 3, and then I still have this leftover 2 underneath. So 2 times 3 is 6 times the square root of 2. So just another way to get the same answer. You would get the same answer if you broke this 12 down into 3 and 4, because then that 4 is going to give you a pair of 2s. So just another way, again, to get the same solution. Quotient property is similar, so we can either take a fraction and pull it into two separate radicals, or we can put them together into one. So really what I would say is if we have something like example 1 here, if you have a fraction under the radical, if you can simplify it, go ahead and do so. But 9 over 64 doesn't simplify. So I'm going to split this into the square root of 9 over the square root of 64, and then I can simplify each of those individually. I know the square root of 9 is 3, and I know the square root of 64 is 8. So 3/8 would be my solution. Whereas with question 2 here, square root of 175 over 5, well, 175, that might simplify. I can use a factor tree and try and simplify that. But the square root of 5 doesn't simplify. So if I turn this into 175 over 5 under the same radical, I can then take 175 divided by 5, which is 35. So now I have the square root of 35, which I would try and simplify, but this is 7 times 5 and neither breaks down any further. Those are both prime. So the solution would be square root of 35. We also have what's called rationalizing the denominator, and this is the process of eliminating a root from the denominator. You're going to do so by multiplying by a form of 1. So we're not allowed to leave roots in the denominator and have something be in what's considered simplified form. So we need to eliminate any roots that we have there. So for example, in question 1, we have the square root of 7/3. So if I use the idea that I described on the last slide, I would see if I could simplify 7/3, but it doesn't simplify. So I'm going to pull that apart into the square root of 7 over the square root of 3. But unlike the last slide, neither one of these roots simplifies. They're both prime numbers. But I'm not totally done because I need to rationalize the denominator. I need to get rid of this square root down here by multiplying by a form of 1. If you have a singular root in your denominator, so nothing that's added or subtracted like you see over here, you can just multiply by that same root, but it has to be a form of 1. So it has to be the same thing on the top and on the bottom. The reason I can do that is now when I multiply across my denominator, I have the square root of 3 times 3, or the square root of 9, which is just 3. So that radical goes away. In the numerator, I have the square root of 7 times 3, which is the square root of 21, and that doesn't simplify. So the square root of 21 over 3. We're not going to simplify that 21 over 3 because this 21 is under a root, this 3 is not. I'm going to go ahead and pause the video here and move question 2 to a new slide so that we can go ahead and see it a little more clearly. Actually, I guess I'm unable to pause. So I'll go ahead and divide my space here. Okay, so something like question 2, where you have addition or subtraction in the denominator, you're going to multiply by a form of 1 again, and what you're going to end up multiplying by is what's called the conjugate, which just means that you change the sign of the denominator. So I'm going to rewrite the original, and then I'm going to multiply by 5 minus the square root of 3. So just change that middle sign. So it was positive, we're going to change it to negative. Whatever I do on the bottom, I also have to do on the top. So what I have here is just the distributive property in the numerator. So 4 times 5 is 20. And then here, 4 times negative square roots of 3 is just 4, or negative 4 square roots of 3. So the 4 is outside, it remains outside. The 3 is underneath, it remains underneath. On the bottom, we're going to distribute again. So I have 5 times 5, which is 25. 5 times negative square root of 3, that's minus 5 square roots of 3. Square root of 3 times 5 is plus 5 square roots of 3. And then square root of 3 times negative square root of 3 is minus the square root of 9. And so this looks really messy, but what happens when you multiply by this conjugate, so when you switch that sign, is that these outside and inside terms will always cancel. So on the bottom, this is really 25 minus 3, which is 22 in the denominator. And then in my numerator, it's 20 minus 4 square roots of 3. Here's another one very similar to the last one that we just saw. So again, we have this root in the denominator that we can't leave there. So we're going to multiply by a form of 1. Because of the subtraction, we're going to use the conjugate. It just means that we switch the sign. So it'll be 6 plus the square root of 2. Whatever we do on the bottom, we also have to do on the top. So then we're going to start distributing. This one's actually a little trickier than the last one because the numerator is going to require us to FOIL as well. So we've got 6 times 2, which is 12. 2 times the square root of 2. Again, this 2 is outside, this 2 is inside, so it's going to stay that way. It'll be 2 square roots of 2. Then square root of 3 times 6. The 6 is outside, the 3 is inside, so it's going to stay that way. And then last, both that 3 and 2 are underneath the radical, so we can multiply them together to get the square root of 6. On the bottom, 6 times 6 is 36. 6 times the square root of 2 is going to be 6 square roots of 2. Negative square root of 2 times 6 is going to be minus 6 square roots of 2. Negative square root of 2 times positive square root of 2, that's going to be negative square root of 4. So then we can clean things up a little bit, but in the numerator, we can't add or subtract any of these roots together. You can only add or subtract like radicals 2, 3, and 6, all of those numbers underneath are different. So this is going to stay 12 plus 2 square roots of 2 plus 6 square roots of 3 plus square root of 6. But on the bottom in the denominator, these guys are going to cancel. And then here, the square root of 4 is just equal to 2. So I have 36 minus 2, which is going to be 34. So just a couple more examples. These ones are more closely related to what we did initially. You've got square root of 5 times square root of 10. I can't simplify either of those individually, so I can put them together and under the same radical. Again, I wouldn't necessarily multiply them to write it as the square root of 50 because I need to break that down with a factor tree. So 10 is 5 times 2. I can pull out that pair of 5s, and then I have a leftover 2 underneath. Question 2, square root of 9 over 11. 9 over 11 does not simplify, so I can pull this apart into square root of 9 over square root of 11. Square root of 9 does simplify. Square root of 11 does not. I cannot leave that radical in the denominator, so I have to rationalize. Here again, it's a singular radical, so I can just multiply it by itself. But whatever I do on the bottom, I also have to do in the numerator. So in the numerator, across the top, 3 square roots of 11, because again, whatever's outside stays outside, inside stays underneath. And then in the denominator, this is going to be the square root of 11 times 11, or square root of 121, which is just 11. Again, I can't simplify these 11s here because this one in the numerator is under the radical. This one in the denominator is not. So you guys have some practice with simplifying radicals on a worksheet for homework tonight, and then we'll continue to practice tomorrow before we start solving equations with square roots.